Hey guys, hello everyone and welcome to the channel. So in this particular video we are going to discuss about the questions from part C of CSIR December 2018 exam. In the previous video I have discussed questions from part B of CSIR December 2018 exam and we have discussed inorganic portion. In that video many of you have asked to discuss part C inorganic portion, so that's what this video is about. So this is going to be all the questions from inorganic portion of part C of CSIR December 2018 exam. Okay, now there were around 20 questions and it takes time to explain each and every question, the concept behind that question and to solve it properly. So that's why the video is quite big. It's around 1 hour video. While editing I got to know that it's around 50 minutes video. So I just hope that this video will be helpful for you for your upcoming exam. Watch this video carefully up till the end, and that's all for this part. And if you are new to this channel, please hit that subscribe button, and if you like this video, give it a like and watch the video carefully. Watch each and every solution carefully. If you have any doubt in any question, you can ask in the comment section, or you can discuss those questions on our Facebook group. The link is given in the description. So just let's continue with the questions.
Fine. So we'll be talking about this question over here. The question says that the product of reaction given below is. So the reaction is given to you and you need to find out the product of it. Okay. So it's very simple. You just need to know the mechanism, the inorganic reaction mechanism and how it takes place. I'll try to explain you guys with the complete mechanism of this particular reaction. Okay. So this COE over here is actually your cyclooctane. Let's try to make that how this reaction will actually be done. So we are having iridium, along with that we have Cl and we have COE and we have PME3 whole thrice. Okay, so that's what we have. Now if you treat it with, like, first of all what will happen, that this COE, that is cyclooctane, that will remove of the reaction, that will go out of the reaction in order to make it coordinatively unsaturated. When the reaction will become coordinatively unsaturated, then only next ligand can come and bind. Okay, so in order to make it coordinatively unsaturated, this thing will happen. So the next species which will be formed will be iridium Cl, and then we have PME3 whole thrice. Now you know that this is a 16 electron species. Now it can easily undergo oxidative addition and it will react with this group, that is this one which is given to you, and we have methyl group attached to it. Okay, so now how this addition will take place actually, that your metal center will bind with this particular carbon, this bond will shift over here like that. So what will be the next species that will be formed? So the next species will be this. So PME3 whole thrice and Cl will be like that, and we'll be having iridium attached to that, and we'll be having CH2. So this is actually your CH2, right? CH2. Then we have, this is at CH, so we'll be writing it CH, O minus and Me. So that's what it will be formed. In the next step, what will happen, that this negative charge will come over here, and this hydrogen, this particular hydrogen, it will liberate from this place and it will go to iridium in order to make it a 18 electron species. Okay, right now also it's not 18 electron, it's 16 electron species, 17 electron species. So in order to make it 18 electron species, this hydrogen will go and bind to iridium. So the next step will be, the next product will be PME3 whole thrice, Cl, iridium, CH2, then we have C double bond O and Me. And over here with iridium we will be having, hydrogen attached. So how this will look in the coordination sphere, if I draw it, so it will actually looks like this. So you will be having iridium, and to that you will be having, so you will be having PME3, sorry, yeah, so PME3 will be there, then we will be having Cl, one Cl is there, then you have PME3 is there. Okay, then you have one more PME3 and one hydrogen directly attached to iridium, and to iridium you also have CH2, C double bond O, CH3. So the directly attached groups, you just need to see that chlorine will also be directly attached, 3 PME3 groups will be attached, one hydrogen will be attached, and one this particular group will be attached. So that is only possible in option number 2. So that's how this reaction will take place, and option number 2 will be the correct option. Fine. Let's take on the other questions and try to see that how they will be solved. Okay, so we'll talk about this particular question over here. It says that the 31p NMR spectrum of cis platinum PET whole thrice Cl2, where this platinum is given as like the isotope of platinum, that is 195. It has 33.8% abundance and it has I value of half, and its other isotopes are given to be NMR inactive. Okay, so now it comprised with satellite peaks of. So this was very debatable question. A lot of answers were given, like lot of discussions were going on for this particular question. I'll give you a very satisfactory answer for this. Okay, I'll try to explain it in very satisfactory way. First of all, just try to understand this, that this particular complex, it comprised of platinum over here, right? Now, platinum can exist in two forms. It is already given in the question that platinum exists in two forms. Let's say one is your platinum isotope. I'm just making it as a star to show you that this star one is NMR active. Okay, so now the abundance of this is given as 33.8%. We all know that. And the other one, the platinum isotope, which is not NMR active, I'll not give star to this. That is just a general platinum, and it will be around, the abundance of this will be around 66.2%, right? So this will be the relative abundance of platinum, like the NMR inactive platinum. Now I value for this is half. This is also is given to you, and I value for this platinum is 0 because it's NMR inactive. So I value is 0 over here. So let's take it 0. Now, in how many, what will be the splitting for the platinum isotope which is NMR active? So to do that, we'll use this formula 2Ni plus 1. So since we have one NMR, like one platinum over there, so N value will be 1, and if you put 1 by 2, and when you do 1, so you will be getting like 2, right? So you will be getting 2 over there. So basically, this is what you will be getting. So 2 into 1 into 1 by 2 and plus 1. That's what you will be getting. And for this, for the NMR inactive one, if you put it in the same formula 2Ni plus 1, so the splitting one, if you do it, so over here you will be getting 2 into 1 into 0 and plus 1. So here you will be getting 2, and over here you will be getting 1. That means this will give you a doublet and this will give you a singlet. So basically, how your platinum spectrum will actually look like. So your platinum spectrum will actually look like something like this. Okay, so it will look something like this. Okay, why is it so? So yeah, because you will be having, okay, so these two like these two peaks which you are looking onto here, these are your small peaks. These will be the smaller peaks. They will be because that is splitting into doublet. Okay, and this single single and long peak, that is because of NMR inactive. Now why this is longer and others are smaller? That is because of relative abundance. Okay, so that intensity or the height of the peak is defined from the abundance of that particular isotope. So over here, the NMR inactive one is having higher abundance, so that's why its height will be more. So what will be the height of it basically? So the height will be 66.2% for the higher one. For the lower one, since the abundance was 33.8, so we can distribute it among two of them. So it will be around 16 point. So it will be around 16.8%. Okay, around 16.8% will be the abundance for these two particular pieces, smaller one piece. Now in the question, remember what it is asked. So in the question it is said that it is comprised with satellite peak of A. So whose satellite peaks are these? That's what you have to tell. So these two peaks which I have marked with this red arrows, these two peaks are actually satellite peaks of this particular longer one, right? So they are satellite peaks of a singlet. So that's why it is, the answer is B. Okay, so this is just, they are asking that whose satellite peaks are these. Okay, so you can just ask yourself like that. So it comprised of satellite peaks of whom? Okay, so they are satellite peaks of that particular singlet. So that's why answer will be singlet. So singlet will be called as the main peak, and the two doublets will be the satellite peaks. So those two satellite peaks are comprised of that singlet. So that's why answer is B. Okay, now let's take back to this, let's take this question over here. It's question number 64. It is said that the reaction of decaborane, okay, so they are asking you about the decaborane over here. So the reaction of decaborane of like B10H14 with acetylene in the absence of in the presence of Et2S. So this is basically the property of your borane and like boron and its hydride, boron hydrides. So it's just a general reaction. If you have studied it, you can answer it up. So it's B10H14. Now when you will react it with 2 moles of Et2S, it will give you, first of all, you will get B10H12. 2 of the hydrogens will be replaced by this. So Et2S will replace 2 of the hydrogens. And then in the next step, you are treating it with acetylene, right? So CH triple bond CH, and over here your 2 moles of Et2S will be removed and hydrogen gas will be evolved, and what you are going to get is this, that is B10H10, and along with that you will be having C2H2, or you can write it like this, that this particular thing becomes C2H10, sorry, C2B10H12. Okay, so that's what your answer should be. So C2B10H12 is the correct answer. So option number 1 is your correct choice for this particular question. Right? Now let's take some other questions. Right, so we will be discussing this particular question for now. Over here it says that the correct order of intensity of DD transition in the complex of 3D transition metal of M+2 configuration, means the oxidation state of metal is +2 given over here, and you have 3 different complexes. One is your aqua complex of that metal, that is MH2O whole 6 2 plus. Then you have 2 more complexes in which you have replaced 2 of the water molecules with chlorine ligands. Okay, now to answer this question, first of all you should know one thing, that this chlorine ligand actually it okay, so this chlorine ligand, it pi donates, okay, pi back donates into the pi back donates to the metal center, and increasing the metal like electron density on the metal, right? Now to understand this thing, what I'm going to do is I'm going to show you that how the molecular orbital of this actually looks like. Okay, so I'll draw the molecular orbital over here. Okay, so I have just drawn the those orbitals which are involved in the transition. Others I have not drawn, just for the d orbital. Whole molecular orbital diagram I'll show you on the right side. The screen, like you will get a slide show of that. So you can see from there that how this transition actually takes place from your T2G to EG orbital. Okay, sorry, T2G star to EG star orbital. So this is actually from your total molecular orbital theory of this particular complex. Now what happens when chlorine pi back donates? When chlorine ligand pi back donates, what happens actually, that it interacts with T2G orbitals only. Why? Because T2G orbitals have pi character and EG orbitals have sigma character, because they are aligned like that. T2G orbitals are aligned like in between of the axis, and EG orbitals are aligned on the axis. So there is a there is an interaction between T2G orbitals and the chlorine filled p orbitals. So that interaction actually helps in the splitting of this T2G and T2G star orbital, and that is why this energy difference changes. Okay, that's why this energy difference changes, and that affects the intensity of DD transition. Now whenever you have chlorine somewhere, whenever you have chlorine in a particular ligand, always remember that the intensity of DD transition will increase from the rest of the ligand. If you have just water molecule as the ligand, then their intensity will be less as compared to the case where you have chlorine atoms, where you have chlorine as a ligand. Okay, so that means both this cis and trans, both of them will be higher in intensity than your water molecule. So both of them should be more than this water. So either your option 1 can be correct or option 3 can be correct. These are only 2 choices. Now you have to decide between cis and trans isomer. Now over here you have to be very careful with the pi donation. Okay, now if both these chlorine ligands become cis to each other, if they become cis to each other, that means they are present like this. So one of the chlorine is on the axial position, let's say, and one of that is on the equatorial position, and the rest of the water molecule you have. Okay, so like that you have. So this is how your cis complex will look like. Okay, so this is how it will look like. Now if you see the donation, or if you see that how these are interacting, the lone pair of electrons, sorry, the p orbitals of these chlorines are interacting. So over there you will see that for the cis one there is a clash. Okay, there is a there is a clash between the ligand orbitals and the metal orbital, because you know that, okay, if I draw xy orbital of the metal, so this is how this xy orbital of the metal will look like. Okay, so let's say I'm just drawing the xy orbital. Okay, let's draw it and understand. This is metal xy orbital. Now your two ligands, your two chlorine ligands are actually attached like 90-degree to each other. So if one of the chlorine is, let's say if it is overlapping like this, if its orbital are overlapping like this, then the other of the chlorine will be 90-degree to it, and that will overlap something like this. Okay, so it will overlap something like this, because this is chlorine and this is chlorine, both should be 90-degree to each other, so they are right. And you can see that there is a clash. Okay, there is a clash of overlapping on this metal orbital. Both of these chlorine atoms are actually trying to overlap with this orbital, which is not possible. Okay, which happens, but now the pi back donation will be less over. Now if pi back donation is less over here, then that means that T2G and T2G star and T2G orbitals will not split that much. So this energy difference will not be that much. Okay, that energy difference will be little higher as compared to the trans one. In the trans one, it won't happen like that. In trans one, they both will be 180-degree to each other, so they will be something like this. I'll just draw to explain you. So this is how two chlorine atoms are actually overlapping over here. Now you can see that the overlap is taking, and there is no clash of orbitals, right? So in the trans one, there is no clash of the orbitals. So if there is no clash of the orbitals, the pi back donation will be more possible over here. If pi back donation is more, the difference between this difference will increase more, and this delta O, or the distance between EG and T2G, will be reduced, right? And if this distance between T2G and EG is reduced, that means there will be more number of transition which will take place from T2G to EG. So there will be more number of transitions which will take place. So over here you can see that in cis one, in the cis one you have a clash of the orbitals. So if the clash of orbital is taking place, then there is like the T2G, that this difference. Okay, I'm just talking about this particular green color difference. So this difference will not be that much. So over here your delta O for cis will be more as compared to delta O of trans. So that's what you are asked with over here. Okay, so they are trying to ask you about the energy difference, that's all. So in this particular question, which answer you will give you, which answer you will take. So it says that for the cis one, you will be having higher energy difference. Why? Because the difference between this T2G star and EG star will be less over here, right? Sorry, it will be more over here. So that's why its intensity will be more as compared to the trans one, and this where there is no chlorine, so that will have lesser. So always remember, chlorine is a ligand which gives pi back donation, and due to pi back donation, these all things are happening. So it was quite clear. If you want to understand this in more detail, you can read Missler and Tar. So these things are given in very much detail over there. So if you guys have that book, you can read it from there. This concept is given over there in detail. Fine. Okay, let's talk about this particular question over here. It says that in compound N3P3F6, the geometry around nitrogen and phosphorus respectively are. So let's try to draw this. So N3P3F6, sorry. So this is how it will be made. So let's first of all make it. Okay, now if you see the coordination number, you can easily find out that nitrogen is sp2 hybridized, right? And it will be planar. Okay, so the geometry around your nitrogen will be planar, whereas the geometry around your phosphorus will be tetrahedral. So the answer should be option number B, where it is said that the geometry around nitrogen and phosphorus are respectively. So you will say that the geometry around nitrogen is planar and the geometry around phosphorus is tetrahedral. It's quite simple and easy question. Let's try to take some more questions and see how they are solved. Let's take these questions, and over here if you see, so this question is directly from your bioinorganic chemistry, and this is just this you can only do if you remember the thing, that's all. Okay, So if you just remember the things, if you memorize these things, you can easily do. So for oxymyoglobin, you have to find out the coordination centers, and then you have to find out the resonance Raman stretching frequency. So you know that oxymyoglobin actually the coordination, like the coordinated, the metal center is coordinated to O2 minus, right? So A is matched with 3. So A is with 3. Okay. Now let's talk about B. So your B in oxyhemocyanin, over there your metal is matched with your eta 2 O2 minus. Okay, where the O2 minus, O2 2 minus is actually a bridging one. So that's why it is. So oxyhemocyanin. Fine. So hemocyanin, that means your B. B is matched with 1. Okay. And now talking about your C, that is oxyhemerythrin. So in oxyhemerythrin, your metal is binded to your HO2 minus. So your C is binded with 2. Okay, so that's how the bond binding is. So just look upon to the options now. So A3, B1 and C2. A3, B1 and C2, it's given in 2 options, in option number 1 and in option number 3. Now you have to also tell about the frequencies. Okay, now you know that if oxygen is in O2 minus, over there the bond strength between oxygen will be more, because oxygen is in double bonded form. So that's why O2 minus, that is for the first one, it will have a higher stretching frequency, that shows around 11105. Okay, so that is matched with Z. So A3 with Z, and then comes your O2 2 minus, where the bond is peroxide peroxy bond. Okay, so peroxide bond, over there it will give you at very lower value, that is around 803. So that is for this. Okay, so that is for Y. And now if I talk about, yeah, so for C it will be X. So now which is the correct option? So first one is your correct option, right? So like that you can do easily. You just need to memorize the values, and the frequencies you need to understand about the, like you just need to know about the binding. Okay, so what kind of bond are actually there. Now to do this particular question, it was very simple. If you just know the structure of P4O6, it says that the hydrocarbon which is analogous to the structure of P4O6. So the structure of P4O6 is like something like this. I'm just going to draw it over here for you guys. Fine. So this is how your P4O6 actually looks like. Now you can see from the structure easily that your phosphorus is, okay, so your phosphorus are trivalent. You can see all these phosphorus are trivalent, means they are bonded with 3 different things, and your oxygens are basically divalent. They are bonded with 2 bonds. Okay, so that means you need something which is trivalent. So over here you can see that, okay, so I'll just tell you that CH3 can make just 1 bond, CH2 can make 2 bond, and CH unit can make 3 bond. So CH will be equivalent to phosphorus, CH2 will be equivalent to oxygen over here, and CH3 you don't need for this now. So how many phosphorus are there? 4 phosphorus and 6 oxygen. So that means you need 4 CH units and 6 CH2 units. So 6 CH2 units and 4 CH units. So that is only possible in your option number 1. So 6 CH2 units and 4 CH units. Okay, mu is given because these are forming the bridging bond, so that's why it is given. Okay, so that's how your correct answer is option number 1. So it was very simple to do this question, right? Fine. So that's all. Fine. So we'll be taking these 3 questions over here, and these all 3 were very easy to solve basically. Let's start with this question number 80 over here. It says consider the following statement for europium plus 3. Europium plus 3, first of all, let's draw the electronic configuration of europium plus 3. So I'm doing it over here. So europium plus 3 will be done like this. Okay, so 1 2 3 4 5 6 7, so like that. So plus 3 will be your F6 actually. So it will be like 1 2 3 4 5 and 6. So that's how it will be. Now just calculate the term for that. Okay, let's try to calculate the term for this, because we need to calculate that. So plus 3 plus 2 plus 1, then we have 0, minus 1 minus 2 and minus 3. So your overall L value will come out to be 3. Your S value will come out to be 3, or 2s plus 1 will come out to be 7, and your J will be L minus S. That will be how much? It will be 3 minus 3, so that will give you 0. 3 minus 3 will be 0. So what will be the term for this? So that will be 7F0. That's correct. So option number B, statement number B is absolutely correct. Now let's talk about statement number C. It says that the observed magnetic moment for uh, like the observed magnetic moment is due to the populated higher J level. Okay, so that's what the question is. Now, if you look upon to the observed magnetic moment of the europium and all, so these things I have taught you guys in the class. Okay, so you can watch my lesson on Academy where I have explained this lanthanides and actinides. Over there I have given all the properties of europium, and there I have explained that how this higher populated J level helps in the magnetic moment of these europium. Okay, so there are two exceptions. Europium and samarium, they have different kind of magnetic behavior except the others one. So this one will also show like that only, and it is not actually spin orbital coupling. It depends upon the temperature basically. So that's why statement C is also correct, is due to high populated J level. So J level is highly populated, so that's why it has observed magnetic moment because of that. Now the point D, it says that at 2 Kelvin its magnetic moment approaches to 0. That is also very correct. I told you that this magnetic moment of europium actually depends upon the temperature. It does not depend that much upon spin orbital coupling over here. Now talking about statement number 1, it says that the positions of sharp band and UV visible spectra of this complex depends heavily on the ligand field. So that is totally incorrect. Any of the lanthanide, they does not depend upon like lanthanides or actinides both. They does not depend upon ligand involvement, because these all are because of the f orbitals. Electrons in the f orbital, and f orbitals are deeply buried inside the nucleus, so they does not affect, the ligand field does not affect them. Okay, so your option number 2 is your correct option. Okay, fine. Let's try to do this particular question. It's very simple. This one also, it's just based upon your analytical technique. It is said that the sample of this particular complex is given to you. It shows 5.6% weight loss at 120 degrees Celsius in that TGA experiment, and identify the complex left after this weight loss. So if you just calculate the atomic weight of this particular complex, I am not going to write it down and calculate over here. I have already done. So it will come around 389 approximately. Okay, you can get around 388 also. So this is how the approximate weight of the compound will come out. Okay, now just take this water to be 1 over there. Okay, so just take this water molecule to be 1. Now talking about this 5.6%, so if you do 5.6% of weight loss, your atomic weight will come out to be around 367. Okay, just take 5.6% of this. How you calculate that? So 5.6 upon 100 into 389. Just calculate whatever value you get, subtract it from 389. So that will give you this. So this is the mass of the this is the weight or the mass of the substance which is left after the weight loss. Okay, you need to find out the weight which is left after the weight loss. So this is what you get after the weight loss. Now if you calculate in the options, if you do the weight, like the molecular weight of this, so that is like NaFe DTA, if you do for that, you will get approximately this much only, approximately 367. So this is the only thing which will be left out after the weight loss. That means what has been lost over here. So your water molecule has been lost in this particular process. Okay, so your option number 2 is correct. One more easy way I'm going to tell you to do this question. It's very simple. Whenever a thermogravimetric experiment is done, basically all these molecules like water, carbon dioxide, or any of these molecules, they evaporate. Okay, and since you are doing at a little higher temperature, you know that this is the boiling point of water is 100 degrees Celsius. So beyond that, this water will actually evaporate. Okay, so the only thing will left out will be anhydrous, that particular sample. Fine. So it's very simple, right? Let's do the other question now. So it says over here that consider the two set of molecules. We have a set A and set B. In set A, if you see, you have aluminum, phosphorus, sulfur and silicon. Oxidation states are different. Aluminum is in +3 oxidation state, phosphorus is in +5 oxidation state, sulfur is in +6 oxidation state, and silicon is in +4 oxidation state. So the oxidation states are different over here. If the oxidation states are different, I already told you guys that ligand exchange, the inertness and lability of the complex depends upon the oxidation state. So as your oxidation state increases, your bond strength between the metal and the ligand increases, and if the bond is stronger enough, it will not break down, it will not react with anything, so it becomes stable, or you can say it becomes inert, and there you will not get that much of ligand exchange. So that will show you slowest ligand exchange. So the slowest ligand exchange in set A will be observed for SF6 complex. So second option should be the correct option. Okay, let's check for the other part also. For the second part, you have barium, calcium, magnesium, strontium. They all belong to same group. That means based upon the size. So when the size of the metal ion is small, you have a stronger bond between ligand and metal over there. Yeah, like the bond strength between metal and ligand is stronger over there, so that will show the slowest ligand exchange. So for that series, you just have to look upon to the size of the metal. So the size of the metal is smallest in magnesium. Okay, so that's why it is verified. So that will be the strongest bond, and that's why it will not react. It will become inert, and that will be slowest ligand exchange rate. Okay, so that's how your answer number 2 is your correct answer. Fine. Let's take some more questions. Okay, so we will take this particular question now. It was the easiest one, I think. It's directly from the notes. Okay, whatever you have studied from the nuclear chemistry is directly from there. It says that match the item given in column 1 with the given in column 2. Now you can easily match them out. Okay, you know that what magic number is. So magic number is for the shell model, right? So this fourth one is for A. So I'm just writing it over here. Then you have liquid drop model. Liquid drop model is basically used to explain nuclear fission, right? So your liquid drop model is for nuclear fission. So B is over here. Now the next one is actinides. You know that the like all the actinides are radioactive. So your third one is for C, and D is threshold energy, that is calculated with the Q value. Okay, so threshold energy depends upon the Q value. So that is D. Now you can just check it. So you have A related with 4, B with 1, then you have C with 3 and D with 2. Okay, so which one is the correct one? Option 1. So you don't have to do anything, it's the correct one. Okay, let's go for the 74 question. Many students were not able to do it. It's very simple. I will try to explain you with one of the method. There are many methods to solve this particular question. I will tell you with a method which I know. If you guys know any other method, you can solve it based upon that. It doesn't matter, but this is one of the method. Okay, first of all, just calculate total valence electron. Okay, so total valence electron, if you calculate, so you have 9 electrons from each rhenium, so 9 into 9, and then you have 5 electrons from the phosphorus, then you have 2 minus charge, right? So okay, so you will be having like 2 from each of the carbonyl. We have 21 into 2, that will come from the carbonyl ligand, and 2 minus charge, so you have to add 2 more. So if you do that, you will get 130. Now you need to calculate a term given as PVE. Okay, so PVE, PEC it is called. Okay, so that is calculated like this. So PEC of a particular complex is calculated like this. So TVE minus N into 12. Okay, so where N is the number of the center, okay, metal center, how much center you have. So you have 130 minus 9 into 12. Okay, so 9 into 12 you know, and if you subtract it, so you will be getting 22. Now this PEC divided by 2 will give you a term. So PEC divided by 2, so 22 divided by 2, that will give you 11. Okay, and 11 you can write in which form, like 9 plus how much, so you can write it like 9 plus 2, right? 11 can be written like 9 plus 2, and you have to relate it with this. So if n plus 1 it is, then it is called proso. If you get n plus 2, it is called nido. If you get n plus 3, that is called arachno. So that is how we relate them. So since it is of the form n plus 2, so that's why it will be nido. So your answer shall be either 3 or 4. Now let's try to see that what kind of structure it will have. Okay, so that is also very easy. You just need to know the structures. Okay, so what is capped square antiprism? So square antiprism look like this. Okay, so you have a square base at the top, then you have a square base at the bottom also. Okay, like that, and it is capped one. That means you have a center over here, and one of the thing will be like this. Okay, so this is how it will be. So total coordination number over here, if you count, so it's 1, 2, 3, 4, and 5, 6, 7, 8, and one more from here, so 9. That is the center. Okay, so you don't have to calculate the center. So you have 9 coordination over here. And what about your bicapped trigonal prism? So trigonal prism looks something like this. So it will be 3-sided like this. Then you will be having, in the similar way, you will be having over here in the bottom side also. So 3 in the bottom. Okay, and bicapped means you will be having two caps, so one here and one here. So if you count down the coordination number, it will be 1 2 3, it will be 4 5 6. Don't count the center, okay? 6, then 7, and then 8. You just have 8. But over here, how many metals you have? You have 9 metals. So 9 metals can only be fixed in this one, okay? So it should be which one? Not bicapped trigonal prism, it should be capped and square antiprism, okay? So your answer should be 3. Like that, easily by applying the simple logic, you can answer as option number 3. Okay, so that's all. That's how it has to be done. Let's take other questions now. Fine. So let's take these two questions. Over here, it says that B2S6 reacts with water to give boric acid and H2. So this is basically the properties of your B2S6. You should study about them. It comes under main group elements. So you can see there were two questions from the boron hydrides, right? One was from the B10H14 kind of thing, and this is the next one. So if you have studied about B2S6, then you can easily do this question. The four options, like it will react with water to give boric acid and H2. It will react with oxygen to give B2O3 with H2. It will react with water to give boric acid and H2O, and it will react with oxygen to give B2O3 and H2O. So that you need to understand, you need to study about the properties, that's all. I have made a course on Unacademy. If you have not prepared yet for main group elements, you can watch that course. There I have included a lot of lessons where you can read them out. That will give you a good revision of this particular topic, right? So basically your B2H6, it reacts with water. It reacts with water to give you boric acid, that is BOH whole thrice, and along with that you will get hydrogen gas. Okay, so this is how the reaction takes place with water. The reaction with oxygen is basically it reacts with oxygen to give you B2O3, and along with that you will get water. So remember, when it reacts with water, it won't give you water. If it reacts with oxygen, it won't give you hydrogen. Okay, so like that you can remember. So which is the correct option? So if you check it, so it will react with water to give boric acid and H2. That is correct. If it reacts with oxygen to give you B2O3 and H2, that is also correct. So option like A and D both are correct. So option number 2 is your correct choice for this. Fine. This was easy one. Now let's take one more easy question. Question number 72. It says that the ligand that binds strongly to the nickel center in 2,2-bipyridine nickel 0 complex is. Now the ligand which have a strong electron withdrawing group will have a strong pi acceptor tendency, and that will bind strongly. Okay, so remember this thing, what? That the ligand which have a strong electron withdrawing group attached to it, if electron withdrawing group is attached to it, then what will happen? It will have a strong pi acceptor tendency. Okay, so it will have strong pi acceptor tendency, and if it has a strong pi acceptor tendency, then it will bind strongly. So that is the logic to solve this particular question. Based upon that, you can easily tell that your option number A is your correct option. Fine. Let's take some more questions and see how to do this. Okay, so we'll talk about this particular question over here. It says that consider the following statements for FeO4 minus. Now, all these statements, like first statement says that it is stable in pH range from 0 to 14. Second says that it is stable in a strongly basic medium. Third says that it is very strong oxidizing agent. Fourth one says that the isomer shift in its mass bar spectrum is more negative compared to that of FeCl3. Now, to do this particular question, you first of all you need to find out the oxidation state of iron. So what is the oxidation state of iron over here in FeO4 minus? So it will be like so iron is in +6 oxidation state, right? And in FeCl3 it is in +3 oxidation state. Fine. So this is done. Now let's see the points over here. So the first one says that it is stable in. So this question you can only do if you know about these things. Okay, that's all. If you don't know about these things, you won't be able to do it. Okay. So now, will it behave as a strong oxidizing agent or not? Oxidizing agent means it will go on so it will go on self-reduction in order to oxidize the other. Reduction means addition of electron. Okay, so the one which can easily accepts electron and it can undergo reduction of itself, and like oxidize the other one. So that's what it is. Okay, so yeah, it can reduce itself from +6 oxidation state. It will try to go to +3 or +2 oxidation state by accepting 3 or 4 electrons. So it will behave as a good oxidizing agent. Okay, so it will oxidize the other things. So third point is very true. So C is true. So C is given in all the options. So that is but obvious. Now talking about the Masber spectrum. Okay, so the isomeric shift, if you see, so since you know that in Fe like in +6 oxidation state it's a D0 complex, and in Fe +3 it's D5 complex. Now you should know that the isomeric shift in the Masber spectrum will be more negative, right? Because you have lesser number of electrons in it, so it will be more negative compared to that of FeCl3. So D is also correct. So C and D both are correct. Now either your option D, like 4, 2 or 1, any of these can be correct. Okay, C is now, we can just neglect C. Now let's talk about A and B. So where it will be more stable. So since it's a good oxidizing agent, it will be more stable in the basic medium. Why? Because you know that acid is like in the if you keep it in acidic medium, acid are itself electron acceptors, right? So they will accept electron, but it does not want to give electron. It is already electron deficient, so it will gain electron. So it will try to be in that particular medium where there are things which are ready to donate their electron. Okay, so base are electrons giver, okay, or they are like electron donator. So you know that in the basic medium it will be very stable. So B is also correct. So your option second should be your correct option, where B, C and D are the correct choice. A will not be correct because it's not it cannot stay stable in pH range less than 7. Okay, it won't be stable in the acidic medium. Okay, let's talk about this particular question. It says that the isomer A and B, okay, in this particular question, isomer A and B undergoes base hydrolysis by forming trigonal bipyramidal intermediate. The correct statement is, so for that, first of all, you need to find out that what is the intermediate actually. So I'll just try to show you that how this reaction is actually taking place. So in the first one, okay, I'll just do it over here. Okay, so you have these complexes. Fine. So just pay focus over here. If you see in the first step, this when you treat it with base, what will happen actually? One of the hydrogen from this will remove and it will make NH. Okay, out of NH2 it will become NH. So it is available like that. Only in the next step we will be having this chlorine ion will like the chlorine ion will be removed from this particular place. So it will go out of the reaction. So elimination of this chlorine ligand is over here. In the next last step, you are treating it with water. So when you treat it with water, it will form like OH over here and NH2 will be formed over here. Okay, so back again. So that is how the reaction is actually taking place. So the question was like the isomers of A and B undergo base hydrolysis. So this is how the base hydrolysis will take place by forming a trigonal bipyramidal intermediate. So this is what the intermediate is. Okay, so this was the intermediate for A. Now the question says that which reacts faster, whether A reacts faster or B reacts faster. So what will happen in B? In the B also same thing will happen. Just the only case will be like okay. So the only thing is that okay. So the only thing which can possible, this is for A. Okay. Now okay, so A reacts faster than B or B reacts faster than A. That's what we need to tell. Now in B, what is happening? In A you have chlorine over here. In B you have chlorine over here in this particular axial bond. Okay. Now if you do for B, you will be having the similar kind of reaction. The reaction mechanism will be same. In that you will be just having chlorine in the the chlorine will be there in the axial bond. Okay. So I'll just try to make it up over here. Now just look upon to this over here. You will see that this particular thing actually, that when you are giving a base to it, this NH2 is getting changed into NH over here. Okay, this is getting changed into NH, and this particular NH remains like that only until this Cl minus is removed. Now on the last step, when you treat it with water, so there are two possibilities which can happen. First is that OH can come and bind at this particular place, and this NH2 will go this NH2 will go towards the, it's actually NH3, okay, so it's not NH2, it's NH3, okay, just let me correct it out. Yeah, so it's NH3. So what will happen now that when you treat it with water, so this NH3 will, it can go to two places. It can go to either this place, okay, and your OH will be formed like this and the rest of the things will remain like this, or the second possibility is that OH will come over here and NH3 will remain at its own place and OH will come over here, okay. So there are two possibilities which can happen. So now which one reacts faster? So the reaction will be much faster in A, obviously, because over here this Cl is being removed due to the trans effect of this particular group, okay, and over here this Cl is getting removed because of the trans effect of this nitrogen. Now you know that like the secondary amine or the secondary NH group is more trans effect giving group than your tertiary one, okay. So that's why A will react faster than B, and B is a mixture of products, okay. So your option number 3 is your correct option, okay. So option 3 is correct option, where it says that A reacts faster than B. Why? Because of the trans effect, and B is the result of mixture of products. You can see that there are two products which are getting formed in B. One where this OH will remain in the axial position, and one where it will remain at the equatorial position. Rest of the thing I have not drawn over here, you can draw it. Okay, so like that the reaction will actually take place. Let's take on the other questions now. So here we'll be talking about these two questions. Over here, this is a question which is asked based upon your carbonyl frequency. It says that match the following complexes with their stretching frequency of carbonyl, carbonyl stretching frequency. So over here you will see that you have 4 different complexes of molybdenum, in which you have carbonyl, three CO ligand and 3 other ligands. Okay, these other ligands are actually your PF3. Okay, then you have POMe3, then you have PPH3, okay, and then you have right, so then you have pyridine. Okay, so these are your 4 ligands. Now these are actually these ligands are called spectator ligands. What is a spectator ligand? Okay, I'll just write it down over here. So spectator ligand. Okay, so this spectator ligand is actually a ligand which does not actually takes part in a particular reaction, but it just takes on a particular coordination site. Now how that will affect this carbonyl frequency? So due to the pi acceptor tendency of these ligands, okay, you just have to look upon to the pi acceptor tendency of these ligands, and based upon that you can easily tell that what will be the carbonyl frequency. So the pi acceptor tendency follows this particular order. So I'm just writing down the order for this pi acceptor tendency. So PF3 is highest in that, then POMe3, and PPH3, and then pyridine. So this is the order for the pi acceptor ability. So this order is for pi acceptor ability of these spectator ligands. Okay, so in PF3 what will happen, that your electron density from metal to complex will be reduced, right? So electron density from metal to complex electron density from the metal in the complex will be reduced, and in that case your electron density on the metal decreases, and as electron density on the metal decreases, your metal carbon bond strength decreases and carbonyl bond strength increases. Okay, so you know, right, so, that pi acceptor, these pi accepting ligands, what they will do, they will accept electrons from the metal center, they will make the metal center electron deficient, and as the metal center becomes electron deficient, your pi back bonding reduces, and if the pi back bonding reduces, your carbonyl frequency increases because bond order increases, and in that case bond strength increases. Okay, so this is how like this will be the same order followed by that. So this A1 will have highest value, so A will be matched with third. Okay, so A will be matched with third one, then B will be matched with the second highest, that is with 2. So B will matched with 2. And talking about C, so C will be matched with the third highest one, that is first. Okay, so C will be matched with first, and D will be matched with fourth. So like that it will be matched. If you see in the options, option number 2 is the correct choice for this particular one. Okay, so it's very simple. You just have to see the pi accepting series, okay, or pi accepting tendency of these ligands, and that will tell you the answer. Okay, now let's talk about this particular question over here. It is also based upon frequency, but over here we have to deal with CN bond stretching. Now we have iron, like in the set A we have A and B, where in A iron is in +3 oxidation state, and in B you have iron in +2 oxidation state. Okay, now you all know that when the oxidation state increases, your back bonding decreases, and as the back bonding decreases, your the stretching, the bond strength of the bond, just like the carbonyl bond, it's similar to your CN bond. Okay, so that bond strength also increases, and then their frequency will also increase. So the one which is more electron deficient, the metal center, where the metal center is more electron deficient, that will have higher frequency. So in among A and B, A will have higher frequency, so A will be more than B. Now talking about C and D, so in C and D, this is your C, where you have NH3 also as a ligand, and this is your D where NH3 is not over there. So now like this is because of the strong field ligand in this. So over here, due to presence of this NH3 as a strong field ligand over here, so that will cause this change in stretching frequency. Okay, so due to the presence of a strong field ligand over here, you will see that the frequency of CO bond, okay, carbonyl frequency, will decrease over here. Why? Because this NH3 will be present in trans to it, and it's a strong field ligand. So like that's why, and like the electron density from the metal, like this NH3 will try to give its electron density towards metal. Metal will have higher electron density, and as the electron density increases in metal, your carbonyl frequency decreases. Okay, so in compound C, you have higher electron density over chromium as compared to D. So among C and D, C will be less than D. Okay, so that's how your correct option will be option number